Hey everyone, this is Dr. Walker. This is video 214 and it is called Electric Potential. So I like to compare electric potential to electric field to help us understand what it is. Let's look back and remember what the electric field tells us. So if we have a source charge, let's call it a positive charge, let's call it big Q, we know that it produces an electric field. And we know that if we place a positive test charge, so we'll call it little q, if we put this charge within the field created by the source charge, and the field points away from that charge, if we put this charge here, it will experience a force in the same direction as the electric field. So it's going to experience a force this way. If we put the test charge further away, then it will experience less force. And this is because there is less electric field. The electric field is weaker at this point. So the electric field tells us how much force that the test charge is going to experience if it is placed within that field. So now we're ready to talk about the electric potential. Let's consider some source charges. Again, it could just be one, but this picture just happens to have a few. So that's just source. So this source is definitely producing an electric field, but it's also producing an electric potential. The electric potential tells us how much potential energy the test charge is going to gain when it is placed within that potential. So you see the similarity, right? The electric field tells us about the force. The electric potential tells us about the energy. So if we put a test charge at this point here, then it will have some potential energy. If we put a test charge over here, it will also have some energy. It will actually have less energy. So we could say big PE here, big potential energy, smaller potential energy. If we put it really far away from the source, that test charge, then it will have a very little bit of potential energy. So the amount of potential energy that it has depends on how much electric potential there is at that point. So we can conclude that there is a stronger electric potential over here closer to the source, and there's a weaker electric potential further away from the source. So this equation over here actually agrees with that and helps explain this. This equation tells us how much electric potential is produced by a charge. So this is our source, this is big Q here, and it's producing this potential all around it. So it produces more potential the closer that you are to it, and it produces less potential the further away that you are. So when you put that test charge at that point, it will have energy. If we look at this equation, it tells us that the electric potential is equal to kq over r, where q is the Coulomb constant, k is a Coulomb constant, q is our source charge producing that potential, and r is how far away that you are from that point. So you can see that the bigger the r, as r gets big, then the potential gets smaller. This equation does assume that the potential is zero at r equals infinity. So this means if you're very far away, where r is close to infinity, then we say that the potential is equal to zero. A couple more things about the electric potential. The units is the volts, which is also designated using the letter capital V. So you can tell by the context what the V represents, whether it represents electric potential or volts. The nice thing about electric potential is it's a scalar, so direction doesn't matter. So that makes it easier to work with. Let's look at 3 questions. The first question says, a 1 nanocoulomb charge rests as shown. Find a potential at point A. So pause the video, take a minute, try this on your own. Think about what equation is relevant here. Let's take a look. So the relevant equation is the potential created by a point charge, right? If it's looking what's the potential over here, well, it's produced by this point charge. So the equation is kq over r. All we need to do is plug in the correct variables. So k is Coulomb constant, 8.99 times 10 to the 9. Q is the charge, the source charge, which is 1 nanocoulomb here. That's our big Q. Nano is the prefix for 10 to the negative 9. And then R is a distance, how far away. So how far away is that point from the charge? It's 1 centimeter according to the diagram. We are going to convert that to meters. So divide by 100, 0.01 meters. And that's it. We plug and chug. And we'll see that the nice thing about these powers of 10 is they cancel out. So you can actually do this using your calculator. 8.99, without using your calculator, 8.99 divided by 0.01 ends up being 899 volts. So that is the potential produced at point A. And we will see this problem again, so keep it handy. We'll do a few more things with it in future videos. Let's look at the next question. We've seen this picture before, but now I'm asking a different question. So it says point B is at a lower blank than point A. We have an electric field pointing downward. Now we do have to assume from this picture that this is a uniform electric field, and usually the question will say that. It's a uniform electric field. That means it's constant everywhere. It's just pointing downward. So if you have a uniform electric field, then you don't have point B at a lower field than point A, since the field is the same everywhere. And let's look at the answer A here, energy. So a point doesn't have energy, right? A charge can have energy, but not a point. So it doesn't make sense to say point B is at a lower energy. So by process of elimination, potential is our answer. But can we understand that? So I do have a note to help us remember and understand this. So the note is that the electric field always points in the direction of decreasing potential. So the electric field is pointing downward. That means that the potential is decreasing. You have a bigger potential at A than you do at B. The way that I like to think about this is I like to visualize the charge plates. And you'll see I'll keep drawing them over and over. I really like to draw them. So I like to draw my charge plates, positive and negative. Because if I draw them, then I know the electric field points to the right. It always points away from the positive charge towards a negative charge. But what I also know is when I have a charge plate, the potential produced by a positive charge is more than the potential produced by a negative charge. So a negative charge actually creates a negative potential. Remember the equation V equals kq over r. This is a scalar. We don't care about direction. There's no direction, but there's a sign. If you have a negative charge, that's a negative potential. So a charged plate will have a higher potential if it's positive, and it will have a lower potential if it's negative. So that helps me remember that, hey, the electric field points towards a lower potential just by drawing those plates. In addition, instead of thinking of these plates as having a positive and negative potential, for simplification, I like to just pretend that this has a positive potential. I'll just give it a number, such as 9 volts. And I'll just say that the negative plate has 0 volts. So it's just out of convenience. This is a lower potential, so I'm just using this potential as my reference point. So I always like labeling it like this. It helps me remember the potential, the electric field, and then if I place a charge in there, what happens to it, etc. Let's look at one final question for this video. When a negative charge is placed in an electric field and starts moving, so which of these happens? So I encourage you to draw the plates that I just drew on the previous slide and use them to help answer the question. So pause the video. Okay, so now let's go ahead and do what I just suggested. We're going to draw those plates again. I told you that I really like them. And so I draw my positive and negative. I'm going to draw my electric field. And now I'm also going to just label these as 9 volts and 0 volts, just convenience. This one's at a higher potential. So now let's see what happens when a negative charge is placed in an electric field and starts moving. So if we put a negative charge here, it's placed in this electric field. A negative charge always experiences a force in the opposite direction as the electric field. So when it's placed in this field, which way is it going to move? It's going to move to the left. So does it move in the same direction as the field? No. Does it move from a point of higher potential to a point of lower potential? It's actually going from a lower potential to a higher potential, as we can see. So that means that its electric potential energy decreases. Now, again, it just helps to visualize it, but think about it. This negative charge is moving towards the positive charges the way that it naturally wants to go under the influence of this electric field. So that means that its potential energy decreases. Remember the book? When it falls the way it wants to, the potential energy decreases. So hopefully the visuals are helpful, and we will keep on going with the topic of electric potential in the next video.